In the previous two modules, we have discussed about connected spaces and disconnected spaces. We have provided so many examples of disconnected topological spaces and also provided example of connected spaces. But most of our examples of connected topological space is based on the connectivity of any intervals of R. In fact, we have proved that R is connected. In fact, any intervals of R is connected and uses the fact that finite product of connected spaces is connected. In this way, we have proved that any Euclidean spaces is connected, but still now we have not got any workable equivalent condition of connectedness. In the next module, we shall provide a very much working equivalent condition of connectednesses which will be applicable in fact all possible cases, which will be called as path connected spaces. We shall prove that a space is connected if it can be joined by a path any 2 points. In fact, we shall say in this condition that the space is path connected and prove that every path connected space is connected. So, let us go to the slide presentation. As we have discussed that it is not very much easy always to prove connectedness. We need some workable definitions or workable conditions. For example, it is difficult very much to prove using usual techniques that punctured plane is connected or sphere is connected. But now what we will define, that will be an easier process to prove the connectedness of practically most of the topological spaces. Definition: let X be a topological spaces and PQ belongs to capital X. A path in X from P to Q is a continuous mapping F from close interval 0 1 to capital X such that f of 0 is equal to P and f of 1 is equal to Q. Note that joining two paths is again a path. In fact, if f is a path from P to Q and G is a path from Q to say another point R, then we can get a new path from P to R, which is first F and then G. In fact, the new path can be defined as f of 2x when x greater or equal to 0, less or equal to half, and g of 2x minus 1 when x greater or equal to half, less or equal to 1. We will discuss it later. Our main definition in this module: a topological space capital X is said to be path connected if for any 2 points PQ belongs to capital X, there exists a path in X from P to Q. That means there exists a continuous function f from 0 1 interval to capital X such that f of 0 is equal to P and f of 1 is equal to Q. In fact, here there is no speciality on the closed interval 0 1. We can take any closed interval because any two closed interval in R are homeomorphic. So, we can take path from any closed interval 0, 1 to x. The following theorem will help us to prove so many spaces are path connected. Theorem: path connectedness imply connectedness. If possible, let X be a path connected space and it is disconnected. Then there exist two disjoint open sets U and V such that X is equal to U union V, where both U and V are non-empty. So choose two points X and Y such that X belongs to U and Y belongs to V. Now as capital X is path connected, then there exists a path from X to Y. That means a continuous function f from closed interval 0, 1 to capital X such that f of 0 is equal to X and f of 1 is equal to Y. Then f inverse capital U and f inverse capital V are the separation of closed interval 0, 1, which is impossible because closed interval 0, 1 is connected. Hence, we have proved that path connectedness implies connectedness. Continuous image of any path connected space is path connected. We have previously proved that continuous image of any connected space is connected. Here we claiming that continuous image of any path connected space is path connected. In fact, if we compose the path with the continuous function, then we can easily say that continuous image of any path connected space is path connected. More formally, let f from X to Y be a continuous surjection and let X be path connected. Let P and Q be 2 points in capital Y. Then there exist 2 points U and V in capital X such that f of U is equal to P and f of V is equal to Q. Now as X is path connected, then there exists some continuous function say phi from the closed unit interval 0, 1 to capital X such that phi of 0 is equal to U and phi of 1 is equal to V. Then f compose phi becomes a path in capital Y starting at P and ending at Q. Rn is a path connected space. In fact, any convex subset of Rn is path connected. To prove this, it is sufficient to show that we can get a path in any convex subset of Rn. For this, let X and Y be 2 points of a convex subset of Rn. Then Tx plus 1 minus Ty is contained in that connected set whenever t less or equal to 1 greater or equal to 0. So, if we define a function f of t is equal to Tx plus 1 minus Ty from closed unit interval 0, 1 to that convex subset of Rn, then we get a path from X to Y, and therefore any convex subset of Rn becomes path connected. We have already told that we can compose two paths. In other way, we can multiply two paths. In the following sense, if capital X is a path connected space and x, y, z in X, let f be a path from X to Y and G be a path from y to z, then the function capital F from 0 1 to capital X defined by f of t is equal to f of 2t when t less or equal to half greater or equal to 0 and is equal to g of 2t minus 1 if t less or equal to 1 greater or equal to half, then capital F is a path from x to z obtained by joining f and g. This path may be called joining of f and g or multiplication of f and g and will be denoted by usually f dot g. We can use this to prove that punchart plane is path connected. So far we have defined path connectedness and established that composition or multiplication of two paths is path. We can use it to prove that punchart plane is also path connected. In fact, if we take any 2 points in the punchart plane, let us consider another point except the origin in the punchart plane. Then from that another point we can get two straight line path to two are previously fixed paths. Then we can get a new path from the previously two fixed points. In this way we can prove that punchart plane is path connected. We can extend this result to the fact that if countably infinitely many points has been deleted from R2, then it still remains path connected. We have proved that punchart plane is path connected. We can use this fact to prove that unit ball in Rn is also path connected. In fact, the mapping x goes to x by norm x from Rn minus 0 to the unit ball is a continuous surjection. And since continuous image of any path connected space is path connected, therefore unit ball in Rn is path connected. So we have produced that R is path connected space, punchart plane is path connected space, unit ball is path connected space. Now we shall prove that if finitely many points from R2 is deleted, then it still remain path connected. In fact, if countably many points from Rn has been deleted, then still Rn remains path connected. If x and y are 2 points after deletion of countably infinitely many points, then still we can draw uncountably many straight lines through x and y which misses those countably infinitely many points. Now we must have two straight lines between them which will intersect and thus get a path from x to y. Hence, if we delete uncountably many points from Rn, then still it remains path connected. As we have proved that union of any number of connected space is connected whenever their intersection is non-empty, In the similar way, we can prove that any number of path connected space is path connected whenever their intersection is non-empty. We are leaving the proof. In the following example, we can prove that every connected open subset of Rn is path connected. Let X be a connected open subset of Rn. Then, given X belongs to capital X, let Ux be the collection of all those points of capital X which can be joined to X by a path in capital X. We want to show that Ux is equal to capital X. Since X is a connected open subset of Rn, to prove that Ux is capital X, it is sufficient to show that Ux is closed as well as open. So, let y belongs to u of x and choose an open ball B centered at y contained in x. Now, if z belongs to B, then we can join y by a straight line in B, and as y belongs to ux, there exists a path in capital X joining y with x. Hence, z can be joined by a path in capital X with y. Therefore, B is contained in ux. This implies that ux is an open subset of x. In fact, if y belongs to ux, then we can have a open ball containing y which is contained in ux, so that ux is an open set. Now, we shall prove that ux is closed as well. To prove this, let y does not belongs to ux, then we can choose an open ball B, no points of which can be joined to x by a path in capital X. In fact, if so happens, then y belongs to ux. Therefore, B does not meet ux. These imply that ux is closed, and therefore ux is equal to capital X, so that any point in capital X can be joined to x by a path in x, and therefore capital X becomes path connected. In case of connectedness, we have proved that closure of any connected set is connected. What happens in case of path connected sets? We also want to know that an example of a connected topological space which is not path connected. In fact, most of the connected topological space are path connected. In the following example, we shall provide an example of a connected space which is not path connected. This will also work as an example of the fact that closure of path connected space may not be path connected. This example is known as topologist sine curve in the literature. Let us define A is equal to all those points xy such that x is equal to 0 and y belongs to -1 to 1, and B is equal to all those xy such that y is equal to sine pi by x and x belongs to 0 1 semi open interval. Then x is equal to A union V is called topologist sine curve. Clearly, x is the closure of B and B is connected because B is the continuous image of closed interval 0 1. In fact, semi open interval 0 1. But we shall prove that x is not path connected. Let us first see the diagram of topologist sine curve. This is as this. Now let us prove that topologist sine curve is not path connected. As we have already told that B is connected being continuous image of semi open interval 0 1. Also x is equal to closure of B. Therefore, capital X is connected. To prove that capital X is not path connected, it is sufficient to prove that no point of capital A can be joined to a point of capital B by a path in capital X. Let A belongs to capital A and possible gamma from I to capital X be a path starting at A and ending at a point of capital B. Since capital A is a closed set in X, we have gamma inverse capital A is closed in the closed unit interval 0 1. Now as 0 belongs to gamma inverse A, it is non-empty. If we can show that it is open in closed interval 0 1, then gamma inverse 0 A is equal to closed unit interval 0 1, so that gamma I is contained in A. Suppose T belongs to gamma inverse A and let us choose epsilon greater than 0, so that gamma of T minus epsilon to T plus epsilon is contained in D, where D is a closed disk centered at gamma T, end of radius half. Then D intersection X is the union of a closed interval on the y-axis and a small part of the curve y is equal to sine pi by x, each of which is homeomorphic to a closed interval. Furthermore, any two of these sets are separated from each other. Therefore, D intersection A is a component of D intersection X. Since gamma T belongs to D intersection A and T minus epsilon to T plus epsilon is connected, we must have that gamma of T minus epsilon to T plus epsilon is in D intersection A. This proves that gamma inverse A is open in closed interval 0, 1 and completes our verification that X is not path connected. We have discussed about path connectedness in this module. One question we will treat in the next module, that which are maximal connected sets or maximal path connected sets in a topological space. With this we end this module and let us pass to the next module.